Drop a red-hot iron sphere onto a block of ice, and heat will inexorably flow outward until both objects reach the exact same temperature. This is the second law of thermodynamics in action. Heat always moves from hot environments to cold ones. But in the 19th century, the physicist James Clerk Maxwell noticed a theoretical loophole that threatened to collapse this otherwise unbreakable rule. This diagram outlines his thought experiment. We have a sealed box split into two separate chambers, holding 10,000 gas molecules. They rest at an equilibrium of 300 Kelvin, which is roughly room temperature. Now imagine a tiny, intelligent entity, later dubbed Maxwell's demon, that opens a central gate exactly when it needs to. It selectively allows only fast-moving hot molecules to pass to the left and slow-moving cold molecules to pass to the right. By simply opening and closing a weightless door, the demon creates a severe temperature gradient out of total equilibrium. It extracts order from disorder without expending any energy, generating free work and directly violating the laws of physics. To see if this theoretical sorting mechanism actually works, we can build a virtual testing laboratory and run the numbers. This dashboard displays our first simulation. We program an active gate to trigger strictly when an approaching molecule's velocity exceeds 600 meters per second, and let it run for 1,000 interactions. Look at how the temperature lines diverge sharply. Chamber A successfully heats to 320 Kelvin, while Chamber B cools down to 280 Kelvin. The system's entropy, its overall level of disorder, has measurably decreased locally. This raises an immediate question. Does the system actually require an intelligent agent to do this, or could a purely passive mechanical setup achieve the exact same result? Here is our second simulation. Instead of a demon, we use a mechanical, spring-loaded trapdoor. It is calibrated to open only when struck by a molecule with a specific kinetic energy, meaning its mass times its velocity squared, exceeding 550 meters per second. We'll run 5,000 molecules through it over a 10-second duration. We see a brief spike in separation, but the line quickly flatlines back to equilibrium. Random, chaotic collisions overwhelm the mechanical spring, entirely destroying the temperature gradient. Pure mechanics cannot sustain localized order. Without an active agent constantly observing and responding to the environment, chaos reclaims the system. The physicist Ludwig Boltzmann provided the underlying mathematics that explain exactly why the mechanical trapdoor failed. This probability curve illustrates his breakthrough equation, S equals K log W. It proves that entropy, denoted by S, is tied to W, the number of possible microscopic arrangements a system can take. A spontaneous decrease in disorder is not strictly impossible. It is simply so statistically improbable in large systems that it practically never happens. But if probability is the only barrier, we should be able to observe these rare ordered states if we shrink the sample size down far enough. Let's isolate a fluid environment at the nanoscale, containing exactly 100 particles resting at 300 Kelvin. On this tracking graph, we can see brief, spontaneous temperature spikes of 5 Kelvin emerging directly from the noisy baseline. These fluctuations happen naturally, lasting only fractions of a millisecond. The second law of thermodynamics acts as a statistical boundary, rather than a rigid wall. Localized entropy absolutely can decrease, provided you stay within strict mathematical limits. The missing variable in Maxwell's paradox has nothing to do with mechanical trapdoors or pure probabilities. The true cost lies in the act of information processing itself. To successfully sort the molecules, the demon must actively measure and store the velocity data of every single particle it encounters. This visualization shows the demon's internal memory capacity maxing out. Every successful measurement it makes to separate the hot and cold molecules requires writing a new bit of data. Eventually, the demon runs out of space. According to Landauer's principle, clearing out this full memory to continue working demands a strict minimum energy cost. Deleting one bit triggers a localized burst of heat exhaust equal to kT natural log 2, the Boltzmann constant times temperature times the natural log of 2. This mandatory exhaust precisely balances the thermodynamic scales. The demon cannot cheat the universe. It simply hides its energy expenditure inside the physical weight of its own data. Today, researchers in nanotechnology actively harness these precise microscopic forces to build molecular motors, allowing them to extract real physical work from their environments. Modern computing and stochastic heat engines treat localized thermal fluctuations not as random noise to be ignored, but as a usable, predictable energy source. The second law of thermodynamics remains unbroken. It was merely incomplete until physicists realized that information itself is a tangible physical property of the universe.